Well, this video is for Math 60 when we're talking about factoring whole numbers or making factor trees or prime factorization. So I put the numbers from 1 to 100 up on the board in this little grid here to talk about prime numbers versus composite numbers. So this is this method that I'm about to do here, this thing that I'm about to do with this grid of numbers, which is to find prime numbers, is called the sieve of Eratosthenes. So, what is a sieve, right? A sieve is something that catches some things but allows other things to fall through, like a colander is another word for a sieve. So what this sieve does is it catches all the prime numbers and it lets all the composite numbers pass through it. So the definition of a prime number is that its only factors are 1 and itself. For example, 5 is only 1 times 5, so long as we're talking about positive whole numbers. Of course, it's 10 times a half and 20 times a fourth and 15 times a third and all these other things. But in terms of whole numbers, it only has 2 factors, 1 and itself. That makes it a prime number. A composite number is defined as a number that is not prime. Okay? Now, the number 1 is defined as neither prime nor composite. Okay? It plays a special role in our number system. It is the identity element for multiplication, and so it doesn't really play much of a role in terms of factorization, figuring out what numbers divide into any of these whole numbers, because 1 will divide into any number. Okay? All right. Oh, and Eratosthenes is a famous Greek mathematician. One of the really interesting things about these ideas about primes and composites, so first of all, they go back thousands of years to the Greek mathematicians, but also they're incredibly important today in computer security. Most cryptographic systems that run on computers and on the internet are based on ideas having to do with prime numbers. There's a really kind of a fascinating story about the mathematicians in the 1970s who developed these methods that allow us to order things online with a credit card without a lot of worry that that credit card number will be stolen. If those things are stolen, they're typically not stolen in transit. They're stolen off of somebody else's server where they haven't been encrypted. Okay? These methods of encryption or coding can keep information secret and very, very secure. Okay, so let's talk about prime numbers. So 2 is the first prime number, the smallest prime number, and the only even prime number because every other even number is divisible by 2. So we'll cross out all of the other even numbers because these are all divisible by 2, which means that they are not prime numbers. And our goal is to find the prime numbers. Okay. All right. So all those even numbers are divisible by 2, which means that they are composite. All right. The next number is 3. Now we can go through and cross out all the multiples of 3. Now all the even ones like 6 and 12 are going to be crossed out already because they're also multiples of 2. But we can go through there and we can go 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 60, 63, 66, 69, 72, 75, 78, 81, 84, 87, 90, 93, 96, and 99. So all those multiples of 3 are also composite numbers, and so therefore they're not prime. So we cross them out. The idea is that we want to circle all the prime numbers, cross out all the composite numbers. Okay, 5 is pretty easy. because every multiple of 5 ends in 0 or 5. So these are all composite numbers because they're all divisible by 5. And these are all composite numbers. We already crossed them out because they are multiples of 2 as well. All right, what's next? 7. Now, we've crossed out everything that's divisible by 2, 3, and 5, and that also covers 4 and 6. So the first multiple of 7 that we're going to run into is going to be 7 times 7. Okay? So let's go through this. There's 7, 14, 21, 28, 35, 42, and there it is, 49. We haven't crossed that out yet. 56, 63, 70, 77 we haven't crossed out yet because that's 7 times 11. What else? 84, 91, which is 7 times 13, and then 98 we already crossed out because it's even. All right. Let's see here. 11, 13, 17, 19. These are all prime numbers. Let's see. Is there anything we left out? We've got multiples of 11. I think we got all those crossed out already. So I think everything that's left here is going to be a prime number. And you can, I'll put a copy of this grid on My Open Math if anybody wants to do this themselves. You can also write down these prime numbers and keep a list of them somewhere. It's really, once we get past 19 or so, it's not all that big a deal. It is helpful to know these prime numbers and to understand how they work. But really, for our purposes, to do the assignments, you're really only going to need this first group right up there. Let's see, where are we? 83, 89, 97. Okay, so there's all the prime numbers, and that process is called the sieve of Eratosthenes. And it really, the whole idea behind using primes in computer security is that this is really the only way to find prime numbers. There are no good formulas for finding prime numbers. And so using this process for really large prime numbers is very time-consuming and really hard to do. And so that's the whole idea behind that, what they call digital cryptography. Okay, so those are the prime numbers. Let's talk about 2, 3, 5, and 7 before we really get started here. And what I want to do is just sort of reiterate some of the things that I was saying in crossing these numbers out. Every even number is divisible by 2 and therefore not a prime number. And all the even numbers end in 2, 4, 6, 8, or 0. Okay? So if you see something like that, that means it's divisible by 2. Now, a number being divisible by 3 is a little bit tricky. Take something like, for instance, let's say 87. Is 87 divisible by 3? Well, there's a little trick that you can do to find out. If you add up the digits, 8 plus 7, which is 15, is 15 divisible by 3? Yes, then so is 87. Okay? It's kind of an interesting little trick. If anybody's interested, I can show you why it works. I'm not sure that now is really the time to get into that, but it is very fascinating. And that's really the big idea of mathematics, is why is something true. It's not just these tricks. It's why does that trick work. Okay? All right. Let's see. So that's 2 and 3. 5 we talked about. Anything that ends in a 5 or a 0 is divisible by 5. Okay? And 7, you just kind of have to test it yourself. Just divide something by 7. All right? And if you get a whole number, then it's divisible by 7. Okay. So now let's talk about prime factorization. So if you've done factor trees, then that's essentially what this is. You can do this as a factor tree. You can do it some other way. But the idea is we want to break a number up into its prime factors. All right, so on the handout, we start with problem 2, 60. Okay? All right, so the first thing to do is to ask yourself what times what equals 60. And it doesn't matter whether you say 6 times 10 or you say 2 times 30, you're going to end up in the same place. Okay, and I'll show you that here in a minute. So let's say we started out with 6 times 10. Are these prime numbers? No. Well, then let's keep going. What times what makes 6? 2 times 3. Those are prime numbers, so we stop and we circle them. Same thing with the 10. It's not prime. It's equal to 2 times 5. And so there's our prime factorization. 2 times 3 times 2 times 5. The order you put these in, not important to me. If you want to get fancy with it and you want to write this as 2 squared times 3 times 5, that's fine. Okay, now what if you had started out by saying, well, what if I did 2 times 30 for my first factors of 60? That's fine. The 2 is prime, so we'll circle it. The 30 is not prime. This is equal to, let's say, 6 times 5. You could have said 3 times 10 as well. It doesn't matter, okay? The 5 is prime. The 6 is 2 times 3. However you go about doing this, you will end up with the same prime factorization, okay? And all of the factor pairs of 60 are made out of these, okay? Here's 2 times 30. Here's 3 times 20. Here's 5 times 12. Okay, there's 10 times 6. There's 15 times 4. All of the factor pairs are made by using these factors in different combinations. We're not going to get into that too much, but I find it fascinating. Okay, so that's problem 2. Let's keep going here. And what I was saying before about knowing whether or not a number might be divisible by one of these prime numbers is helpful to try to split things up. Okay? Let's see here. Problem 4, 99. Okay. Well, again, you can just start this any way that you want. All right? I mean, I recognize this as 9 times 11. Anything that's a double digit like this, like 22, 33, 44, that means it's a multiple of 11. So this has to be 9 times 11. The 9 is 3 times 3, and that's it. We're done. There's the prime factorization, 3 times 3 times 11. Now, sometimes people like to do it this way. You take 99, and you divide it by 11 and get 9, and then you divide that by 3 and get 3, and then here's your prime factorization. It's the same exact thing, it just looks a little bit different. Okay? And what I was saying before, however you go about doing this is up to you. Okay? The key is to come out with these factors. Okay, let's see here. Problem 6. Now, 144. This has a lot of factors in it. Okay, well, it's an even number, so let's just divide it by 2. And you can use your calculator to do 144 divided by 2, but you can see 2 goes into the 14 7 times, 2 into 4 goes twice. So this is 2 times 72. The 2 is prime. Let's leave it alone, okay? Now the 72 is also even, so let's just keep dividing by 2 as long as we can. Okay, so there's all the 2's, and then we've got a 9 down here. That means we're going to do 3 times 3. So there's our factorization. 2 to the 4th times 3 squared, or 2 times 2 times 2 times 2 times 3 times 3. Okay. Let's see here. All right. let's do problem 10. This is a pretty large number, 700. And I would start simple with this. What times what is 700? I wouldn't get too fancy. 7 times 100. Pretty straightforward. The 7 is prime. We'll put a circle around it. 100, 10 times 10. And again, you could use 4 times 25. You could use 5 times 20. It doesn't matter. 2 times 50. You're going to end up in the same place. This 10 is 2 times 5. That 10 is 2 times 5. And there's our prime factorization. 2 times 2 times 5 times 5 times 7. Okay. What else? Oh, problem 16 is kind of interesting. So now, this number is not an even number, so it's not divisible by 2. It doesn't end in 5 or 0, so it's not divisible by 5. What about 3? Now, you can just go ahead and divide it by 3 on your calculator, and that's straightforward enough. The trick says add these numbers up. 1 plus 1 plus 1 is 3. Is that divisible by 3? Yes. So that means 111 is divisible by 3. Let's see, how many times is that going to go in there? That'll go in 3 times with 2 left over. So that should be 3 times 37. And 37, I believe, is prime. I've of course erased my list of prime numbers, but 37 is not divisible by 2, not divisible by 3, 5, or 7, and that pretty much does it. Because once you get larger than the square root of a number, you can stop checking. There's some pretty interesting reasons for why that is, but again, it's kind of hard to do in a video, and so I don't want to take the time to talk about it right now. But if you have any interest in this, I would be happy to talk with you about it. All right, let's see here. 16, 18. Well, 196 is kind of a large number. I don't know what the factorization is going to look like, but I do know that it's an even number. So this is 2, and let's see, that'll be 98. 2 times 98. And this is also an even number, so this is 2 times 49, and 49 is 7 times 7. So there we go. 2 times 2 times 7 times 7. So it's good to know your times tables when you're doing something like this, you know. I mean, I knew that 37 was prime because I know that 5 times 7 is 35, you know, and so on. I also recognize this 49 as being 7 times 7. All right, let's keep going here. Now we've got some big numbers. Problem 20, 3,458. And again, you can start any way you want on these, okay? The important part is to get down to prime numbers. So I'm going to start with the 2 here. Let's see what we got. 17, 29, I believe, right? 17 and then 2, 9. Yeah. Now, 2 times 1729. 1729. It's not even. It's not divisible by 5. Let's add them up and see if it's divisible by 3. 10 and 9 is 19. It's not divisible by 3. And you can do that just with the calculator, you know. You can take 1729 divided by 3 and see, you don't get a whole number. Okay. What else? What about 7? 1729 divided by 7. There it is. 7 times 247. Now, 247... 247 is 13 times 19. Well, that's a sneaky one. Okay? Because this 247 looks like it could be prime because it's not divisible by any of these numbers. It's not divisible by 11 either. That's the next thing I tried. But then before I gave up, I said, well, let's try 13 or 19, see what happens. I could have tried 17 as well. So in the end, here's our prime factorization. 2 times 7 times 13 times 19. And that's actually how this computer security thing works. They use these numbers that are called pseudo-primes. So this is not a prime number. It's the product of two primes. And trying to find out which two primes is a really tricky business. And that is what drives the security of the information that's encrypted using these methods. Okay, again, that's not something we have to worry about. I just find it interesting. Okay, let's see, we've just got a couple more here. Problem 22, 715. All right, so that's divisible by 5. So let's go ahead and do that. Let's see, what are we going to get out of that? 143. Now again, 143 is not divisible by 2 or 3 or 5. And I suspect if we divided that by 7, we wouldn't get a whole number either, because I suspect that this is 13 times 11. 143 divided by 7, not a whole number. But 143 divided by 11 is 13. Yeah. So this is 11 times 13. So don't give up after you get past here. Do go on. For our purposes, you could stop at 19. I'm not going to get too crazy with these, giving you things that are, products of prime numbers that are bigger than 19 and so forth. All right, let's see here. I think we just got one more to look at. What is that one? 252. Okay, so that's an even number, and that is 126. Okay, well this is also an even number, and so that's 63. And then here's where your times tables come in handy. 63 is 7 times 9. So this is 2 times 2 times 7 times 9. Okay, so I will get this assignment posted for you with an answer key. And as always, if you have any questions about it, please let me know. Thanks.